In this video, we will talk about inverse of a matrix and how to solve linear equations using inverse of a matrix. Hello friends, you are watching YouTube channel Number Collage. This channel features easy to understand concept videos on mathematics. Determinant of a matrix. Suppose matrix A is 1 minus 3, 2, 5. Then the determinant made out of the elements of matrix A is known as determinant A, which will be determinant 1 minus 3 to 5. Similarly, if a matrix B is 1 minus 1 0 3 2 minus 1 4 3 2 is a 3 by 3 matrix, the determinant made out of the elements of matrix B, which will be 1 minus 1 0 3 2 minus 1 4 3 2, is called determinant of matrix B. Singular and non-singular matrix. Consider matrix A 2 1 4 2. Its determinant will be determinant A equals 2 1 4 2. We can evaluate it. It will be 2 2s are 4 minus 4. So the value is 0. So when the value of determinant of a matrix is 0, the matrix is called a singular matrix. Consider another matrix B, which is 1 1 1 3 3 3 1 3 2. Its determinant will be determinant B equals determinant 1 1 1 3 3 3 1 3. Let us evaluate it. It will be this one multiplied by its minor, which will be 3 2s are 6 minus 3 3s are 9, then minus sign this one and its minor, it will be 3 2s are 6 minus 3 1s are 3, then plus this one multiplied by its minor, 3 3s are 9 minus 3 1s are 3, it will be minus 3, this will be minus 3 and this will be plus 6, so it will be 0. Since determinant of matrix B is 0, we say that matrix B is a singular matrix. If the value of the determinant of a matrix is not 0, then that matrix is called non-singular matrix. Let us see how to check a matrix to be a non-singular matrix. Consider a matrix A, which is 1 4 6 9. Its determinant will be 1 4 6 9. Its value will be 1 multiplied by 9 minus 4 multiplied by 6, which is 9 minus 24, which is minus 15. And since this value is not equal to 0, we can say that matrix A is a non-singular matrix. Consider another matrix B, 1 minus 1 2 2 minus 3 1 3 minus 2 minus 1. Its determinant will be minus 1 2 2 minus 3 1 3 minus 2 minus 1. Its value will be this one multiplied by its minor, which is 3 minus minus 2, that is plus 2, then minus plus this one multiplied by its minor, which is minus 2 minus 3, plus this 2 multiplied by minus 4 plus 9. It will be 5 minus 5 plus 2 multiplied by 5. So this 5 gets cancelled and we get 10. Now since the value of determinant of B is not equal to 0, we can say that matrix B is a non-singular matrix. Minor of an element of a matrix. Consider a matrix A equals 1 minus 2 minus 3 3. We have to find minor of every element of this matrix A. Suppose we want to find the minor of this first element of the matrix. So we will hide the first row and first column, and what remains will be the minor of element 1, which is 3. Next, suppose we want to find the minor of the second element minus 2 of this matrix. Then we have to hide the first row and second column, and what remains is minus 3. So the minor of element minus 2 will be minus 3. Suppose we want to find the minor of the third element minus 3 of this matrix, then we have to hide the second row and first column passing through minus 3, and what remains is minus 2. So minus 2 is the minor of element minus 3. Suppose we want to find the minor of the fourth element of matrix A, which is 3. We have to hide the second row passing through 3 and second column passing through 3. What remains is 1. So 1 is the minor of the fourth element 3 of matrix A. So this is how minor of an element of a 2 by 2 matrix is found out. In short, if you want to find minor of every element of a 2 by 2 matrix A minus 1, 2, 3, minus 4, then you can find it this way. Suppose you want to find minor of minus 1, then the element diagonally opposite to minus 1, which is minus 4, the minor of element minus 1. So minor of minus 1 will be minus 4. Similarly, if you want to find minor of this second element 2, then the element diagonally opposite to 2, which is 3, becomes the minor of element 2. So therefore, minor of element 2 will be 3. Similarly, minor of the third element 3 will be element which is diagonally opposite to this 3, which is this 2. And finally, minor of the fourth element, which is minus 4, will be the element which is diagonally opposite to minus 4, which is minus 1. So minor of element minus 4 is minus 1. So in short, the element which is diagonally opposite to a specific element is the minor of that specific element. This is true in a 2 by 2 matrix only. Now let us understand how to find minor of an element of a 3 by 3 matrix. Consider a 3 by 3 matrix A, which is minus 1, 2, minus 3, 0, 1, 4, minus 5, 2, minus 3. This is a 3 by 3 matrix. We have to find the minor of every element of this matrix. Let us see how to find it. But before that, remember, minor of an element of a matrix is always a determinant. Suppose we want to find the minor of this element minus 1. We have to hide the row passing through minus 1 and the column passing through minus 1, so that we get the minor of the element minus 1 as the determinant formed by the unhidden elements 1, 4, 2, minus 3. So the determinant 1, 4, 2, minus 3, which can be evaluated as minus 3, minus 8, that is minus 11, will be the minor of element minus 1. So minus 11 is the minor of element minus 1. Suppose we want to find the minor of another element of the 3 by 3 matrix A. Say for example, we want to find the minor of element 4. Then we have to hide the row passing through this 4 and the column passing through this 4. So we get the minor of element 4 in the form of a determinant of the unhidden elements minus 1, 2, minus 5, 2. So the determinant minus 1, 2, minus 5, 2, which can be evaluated as minus 2 plus 10, that is 8. So 8 will be the minor of element 4. So this is how minors of elements of a 3 by 3 matrix are found out. Now we will understand how to find cofactor of an element of a matrix. Consider a 2 by 2 matrix A, which is minus 2, 1, 3, minus 4. We are going to find the cofactor of every element of this matrix. That is, we will write a cofactor matrix of this matrix A. The cofactor matrix is the matrix of the minors of each element of the matrix with proper sign. So, cofactor matrix of A will be a matrix of the minors of these elements with proper sign. Now first let us write the minors of each of these elements. Minor of minus 2 is minus 4. Minor of 1 is 3. Minor of 3 is 1. And minor of minus 4 is minus 2. Now we have to give proper signs to these elements so as to get the cofactor matrix of A. Now how to give the proper signs? For that we will multiply each of these minors by minus 1 raised to the position of the element minus 2, which is the first row and first column. So we will raise minus 1 to 1 plus 1, first row, first column, multiplied by. Then we will multiply this 3 by minus 1 raised to. Now the position of this 1 is first row, second column, first row plus second column, multiplied by this 3. Now we will multiply this minor 1 by minus 1 raised to the position of this 3, which is second row, first column, second row plus first column, multiplied by 1. Now we will multiply this minor minus 2 by minus 1 raised to the position of this minus 4, which is second row, second column, that is second row, second column, that is 2 plus 2, multiplied by this minus 2. This will be now minus 1 raised to 1 plus 1, which is 2. Now 2 is an even number. So even power of minus 1 is plus 1. So it will be plus of minus 4. Then 1 plus 2 is 3, which is an odd number, and odd power of minus 1 is minus 1. So it will be minus of this 3. Next, 2 plus 1 is 3. 3 is an odd number. Odd power of minus 1 is minus 1. So it will be minus of this 1. And finally, 2 plus 2 is 4. 4 is an even number, and even power of minus 1 is plus 1. So we write plus here, multiplied by this minor minus 2. So this is how we can write the proper signs to the corresponding minors of the elements of matrix A. So the cofactor matrix finally will become minus 4, minus 3, minus 1, and minus 2. So this is how we can write the cofactor matrix of a given 2 by 2 matrix A. Here we can avoid the calculations of minus 1 raised to the powers even, odd, even, etc. by simply writing the signs first, plus, which will be this plus, then this minus, then this minus, and then this plus, succeeded by the corresponding minors minus 4, 3, 1, minus 2. So we can make use of this shortcut. Writing a cofactor matrix. Let us see how we can directly write the cofactor matrix. Consider a 2 by 2 matrix A 9 minus 3 7 2. Its cofactor matrix A will be, first we will put the proper signs. The sign of the first minor is plus, that of the second minor minus, that of the third minor minus, that of the fourth minor plus. Next we will write the minors. Now the minor of 9 is 2, which we write here. Then minor of minus 3 is 7, which we write here. Then minor of 7 is minus 3, which we write here. And minor of 2 is 9, which we write here. So our cofactor matrix will become 2 minus 7 3 9. We can remember this method even in this way. First write, or you can simply write the minors first, which are the minor of 9 is 2, the minor of minus 3 is 7, the minor of 7 is minus 3, and the minor of 2 is 9. Next, you simply have to change the signs of the non-diagonal minors, which are 7 and minus 3, so that in the cofactor matrix of A, the sign of this minor 7 will become minus, and that of minus 3 will become plus. So this is how you can decide the signs of the minors of the cofactor matrix of a 2 by 2 matrix. Now we will understand how to write a cofactor matrix of a 3 by 3 matrix. Consider matrix A, which is 1 2 minus 3 minus 1 3 minus 2 4 2 1. First we will write the minors of the elements of this 3 by 3 matrix A. So the matrix of minors of matrix A will be 3 plus 4, then minus 1 plus 8 minus 2 minus 12, 2 plus 6, 1 plus 12, 2 minus 8 minus 4 plus 9 minus 2 minus 3, 3 plus 2. So which will become 7 7 minus 14 8 13 minus 6 5 minus 5 and 5. Now we have to give proper signs to the values of these minors, after which it will become a cofactor matrix. So the cofactor matrix A plus minus plus minus plus minus plus minus plus, which will finally become 7 minus 7 minus 14 minus 8 13 6 5 5 and 5. So this is our cofactor matrix A. You have to remember the pattern of the signs of the values of the minors, which is you have to start with plus, then minus, then plus minus plus minus plus minus and finally plus. That is, you have to start from plus and alternately you have to write minus plus minus plus minus plus minus plus, like that, and you will get the proper signs of the minors of the 3 by 3 matrix A. So this is how you can directly write the cofactor matrix of a 3 by 3 matrix without doing the calculations of minus 1 raised to the even power or odd power, so on and so forth. Let us understand adjoint of a matrix. Adjoint of a matrix is the transpose of the cofactor matrix. Consider a 2 by 2 matrix A, which is minus 1 2 3 minus 4. Its cofactor matrix will be, first we will put proper signs. They will be plus minus minus plus. Now we will write the values of the minors of the elements of matrix A. So the value of minor of minus 1 is minus 4, then minor of 2 is 3, minor of 3 is 2, and minor of minus 4 is minus 1. So the cofactor matrix will be minus 4, minus 3, minus 2, minus 1. Now we will write its adjoint. Adjoint of A will be the transpose of the cofactor matrix. So it will be minus 4, minus 2, minus 3, minus 1. So this is how we find adjoint of a 2 by 2 matrix A. Now we will consider a 3 by 3 matrix B, which is 1, minus 2, 3, 4, 2, minus 1, 3, 0, minus 5. Its cofactor matrix will be, first we will write the proper signs. Those will be plus, minus, plus, minus, plus, minus, plus, minus, plus. Now we will write the minors of the elements. So minor of element 1 is minus 10 minus 0, that will be minus 10. Minor of minus 2 will be minus 20 plus 3, that will be minus 17. Minor of element 3 will be 0 minus 6, so that will be minus 6. Minor of element 4 will be 10 minus 0, so that will be 10. Minor of element 2 will be minus 5 minus 9, that will be minus 14. Minor of element minus 1 will be 0 plus 6, so that will be 6. Minor of element 3 will be 2 minus 6, that will be minus 4. Minor of element 0 will be minus 1 minus 12, that will be minus 13. Minor of element minus 5 will be 2 plus 8, that will be 10, which will be minus 10, 17, minus 6, minus 10, minus 14, minus 6, minus 4, 13, 10. So this will be the cofactor matrix, and its adjoint will be adjoint B. It will be transpose of the cofactor matrix. So we write minus 10, minus 10, minus 4, 17, minus 14, 13, minus 6, minus 6, 10. So this will be the adjoint of P. Now that we have understood how to find adjoint of a matrix, let us understand how to find inverse of a matrix. But before that, let us see what is inverse of a matrix. Suppose A be a non-singular matrix, which means that determinant of A is not equal to 0. Then there exists another matrix of the same order known as inverse of a matrix and written as A to the power minus 1, such that A multiplied by A inverse equals an identity matrix equals A inverse multiplied by A. The matrix A inverse behaves like reciprocal or multiplicative inverse in a number system. The inverse of a matrix A is written as A to the power minus 1, and it is read as A inverse. For finding inverse of a matrix, it is must that A should be a non-singular matrix, which means its determinant is not equal to 0. A inverse can be found out by a formula. A inverse equals 1 upon determinant of A multiplied by adjoint of A. So with the help of this formula, we can find inverse of any non-singular square matrix. We have to find inverse of a 2 by 2 matrix A, which is 1 minus 2 3 0. First let us find determinant of A, which will be 1 minus 2 3 0, which will be 0 minus minus 6, which is 6. And since determinant of A is not equal to 0, it implies matrix A is a non-singular matrix. Therefore, its inverse exists. Now let us find inverse of matrix A. For that, first let us find out the matrix of the minors of matrix A. We will not get into the details of finding the minors of a 2 by 2 matrix. We will directly write the values of the minors. So the matrix of the minors will be 0, 3, minus 2, 1. We will give proper signs to these minors and we will write the cofactor matrix of A. So let us first write the proper signs. For a 2 by 2 matrix, we have learned the proper signs are plus, then minus, minus, and then plus. Next to these signs, now we will put the values of the minors. So they will be 0, 3, minus 2, and 1. Therefore, the cofactor matrix will be 0, minus 3, 2, 1. Now we will write adjoint of matrix A. It will be the transpose of the cofactor matrix, which will be 0, 2, minus 3, 1. Now that we have found adjoint of matrix A, we will write the formula to find the inverse of matrix A. We have A inverse equals 1 upon determinant of A into adjoint of A. So it will be 1 by the value of determinant is 6. So therefore we write 1 by 6 and multiplied by adjoint of A is 0, 2, minus 3, 1. So the required A inverse will be 0 upon 6 is 0, 2 upon 6 is 1 by 3, minus 3 upon 6 is minus half, and 1 by 6 is 1 by 6. So this is the inverse of matrix A. We have to find inverse of a 3 by 3 matrix A, which is 3 minus 3 4, 2 minus 3 4, 0 minus 1 1. Determinant of A is 1. I will not get into the details of finding the determinant. You know how to find the value of the determinant, which is not equal to 0, which implies that matrix A is a non-singular matrix and hence its inverse exists. Now we will find inverse of this 3 by 3 matrix. For that, first let us find the matrix of the minors of determinant A. We will also not go into the details of finding minors of the elements of a 3 by 3 matrix. We have already studied that and understood that. So here I will directly write the values of the minors. So these are 1, 2, minus 2, 1, 3, minus 3, 0, 4, minus 3. Next we will write the cofactor matrix of matrix A. So the cofactor matrix will be, first we will write the proper signs of the corresponding minors. So the proper signs will be plus, minus, plus, minus, plus, minus, plus, minus, plus. Now we will put the values of the minors. So 1, 2, minus 2, then 1, 3, minus 3, then 0, 4, and minus 3. So that gives us the cofactor matrix as 1, minus 2, minus 2, minus 1, 3, 3, 0, minus 4, minus 3. Next we will write adjoint of A, which will be the transpose of this cofactor matrix. So it will be 1, minus 1, 0, minus 2, 3, minus 4, minus 2, 3, minus 3. Now that we know adjoint of matrix A, we will write the formula to find the inverse of matrix A. We have A inverse equals 1 by determinant of A into adjoint of A. So that will be equal to 1 upon determinant of A is 1 into adjoint of A, which means this matrix. So finally A inverse will be this 1 multiplied by this adjoint of A, which will be same as the adjoint of the matrix, that is 1 minus 1 0 minus 2 3 minus 4 minus 2 3 minus 3. So this is the inverse of 3 by 3 matrix A. If A equals 3 1 1 2, which satisfies the equation A square minus 5A plus 7I equals 0, we have to find A inverse. We are given that equation A square minus 5A plus 7I equals 0 is satisfied by this matrix A. We will multiply this equation throughout by A inverse. So this will be A square will be A into A multiplied by A inverse minus 5 into A inverse plus 7I into A inverse equals 0 into A inverse is 0. This will be A into I, because we know that A into A inverse is I, minus 5 times we know that A into A inverse is I, plus 7I into A inverse is A inverse, because the identity matrix I behaves like number 1 in a number system. This is equal to 0. Now A into I will be A minus 5I plus 7 into A inverse equals 0. So that will be 7A inverse equals, we will send this 5I and A to the right. So it will be 5I minus A. It will be 5 multiplied by the identity matrix 1 0 0 1 minus the matrix A, which is 3 1 1 2. So it will be 5 minus this 3, 5 into 0 0 minus 1, 5 into 0 0 minus 1, 5 into 1 5 minus 2. So this will be 2 minus 1 minus 1 3. So 7A inverse equals this matrix. So therefore we get A inverse equals 1 upon 7 multiplied by this matrix, which is 2 minus 1 3, which will be 2 by 7 minus 1 by 7 minus 1 by 7 3 by 7. So this is the value of A inverse. Consider a 2 by 2 square matrix A1 B1 A2 B2 multiplied by a column matrix XY equals a column matrix C1 C2. The pre-matrix has order 2 by 2. The post matrix has order 2 by 1, and the right hand matrix has order 2 by 1. Now since number of columns of the pre-matrix equals number of rows of the post matrix, this matrix multiplication is possible, and the resultant of the matrix multiplication will be a matrix of order 2 by 1. So the matrix multiplication will be a1x plus b1y, a2x plus b2y, which is a 2 by 1 matrix, equals c1 c2. Now by equality of matrices, we will write a1x plus b1y equals c1 and a2x plus b2y equals c2. But these are nothing but linear equations in two variables x and y, and this is known as the matrix form of these linear equations. Consider a matrix multiplication of A1, B1, C1, A2, B2, C2, A3, B3, C3, which is a 3 by 3 square matrix multiplied by a column matrix X, y, z. Suppose this matrix product is equal to another column matrix d1, d2, d3. Now this column matrix has order 3 by 1 and this column matrix has order 3 by 1. Now the number of columns of the pre-matrix is equal to the number of rows of the post matrix. Therefore, this matrix product is possible, and the resultant of this product will be a matrix which will have order equal to 3 by 1. So this matrix product will be a1 b1 c1 multiplied by xyz. So that will be a1x plus b1y plus c1z, then a2x plus b2y plus c2z, then a3x plus b3y plus c3z, whose order is 3 by 1, which will be equal to the matrix on the right hand side d1, d2, d3 of order 3 by 1. Now, by equality of matrices, we can write a1x plus b1y plus c1z is equal to d1. a1x plus b1y plus c1z equals d1. Then a2x plus b2y plus c2z equals d2, and a3x plus b3y plus c3z equals d3. But these are nothing but linear equations in three variables x, y, and z, and this is known as the matrix form of these linear equations in three variables. Suppose a1x plus b1y equals c1 and a2x plus b2y equals c2 are the two linear equations in variables x and y. First, we have to write these equations in the matrix form. For that, we will pick the coefficients of x and y and write the square matrix a1 b1 a2 b2. Then we will multiply this coefficient matrix by the variable matrix, which is a column matrix x, y. We will equate this product to the column matrix of the constants c1, c2. We will name this coefficient matrix A and this variable matrix as x, and we write the product AX as B. Now we will multiply this equation AX equals B by A inverse. So we write A into A inverse equals B into A inverse. Now we know that A into A inverse is I. So it will be I x equals A inverse into B. But I into x is nothing but x, which is the variable matrix xy, which equals A inverse B. Now we know matrix B, we have to find A inverse from the matrix of coefficients, and that will give us A inverse B. We will perform the product of A inverse B, which will give us a column matrix. Now X is the column matrix X, Y, and A inverse B will be also a column matrix, say P, Q. So now by equality of matrices, we can say that X equals P and Y equals Q. So this will be the solution of these two linear equations in two variables. Similarly, suppose we have three linear equations in three variables a1x plus b1y plus c1z equals d1, and a2x plus b2y plus c2z equals d2, and a3x plus b3y plus c3z equals d3. Then we will write these equations in the matrix form as a1 b1 c1 a2 b2 c2 a3 b3 c3, which is the coefficient matrix, and the column matrix, which is the variable matrix x, y, z, which will be equal to the column matrix of the constants d1, d2, d3. We will name this coefficient matrix as A and this variable matrix as x, which equals the constant matrix, which is matrix B. Now we will multiply this equation by A inverse throughout. So we write A inverse into A into X equals A inverse into B. Now A inverse into A is nothing but I, so it will be I multiplied by X, which equals A inverse into the constant matrix B. But I into X is nothing but X, which is the column matrix of the variables X, Y, and Z, which will be A inverse into B. Here, matrix B, which is the column matrix, is known. We only have to find A inverse from the coefficient matrix A, and the product of A inverse and B will be a column matrix of constants which we can equate with the variables x, y, z so as to get the values of the variables. So by equality of matrices we will finally get the values of the variables as x equals suppose p, y equals q, and z equals r. So this will be the solution of these three linear equations in xyz. So this is how we can make use of matrices and the inverse of a matrix to solve linear equations in two variables or three variables. Solve 3x plus y equals 1, 5x plus 2y equals 3. These are linear equations in two variables x and y. We have to find the values of x and y. So we write these equations in the matrix form: 3, 1, 5, 2 multiplied by the matrix of variables x, y equals the matrix of constants 1, 3. We name this matrix A and the matrix of variables as x and the constant matrix as B. So the matrix of variables x will be 1 by A into B, that is A inverse into B. Okay, first we will find the value of determinant A, which will be determinant 3, 1, 5, 2, which will be 3 2s are 6 minus 5 1s are 5, which will be 1. Now we have to find A inverse. For that, first we will write the cofactor matrix of A. So first we will write the signs, the proper signs of the minors, which will be plus, minus, minus, and plus. Next we will write the minors of the elements. So the minors will be 2, 5, 1, and 3. So the cofactor matrix will be 2 minus 5 minus 1, 3. Adjoint of A will be the transpose of this cofactor matrix. So it will be 2 minus 1 minus 5, 3. So A inverse will be 1 upon determinant of A into adjoint of A. So that will be 1 upon determinant of A is 1 into adjoint of A is 2 minus 1 minus 5, 3. So A inverse will be 2 minus 1 minus 5, 3. Okay, now we write this x is the column matrix or the matrix of variables x, y. Matrix A inverse is 2 minus 1 minus 5, 3 multiplied by matrix B, which is column matrix 1, 3. So this matrix multiplication will be 2 minus 3 and minus 5 plus 9. So which will be a column matrix minus 1, 4. Now by equality of matrices we write x equals minus 1 and y equals 4. So this is the solution of these linear equations in two variables. Solve by matrix method. 3x plus y plus 2x equals 3, 2x minus 3y minus z equals minus 3x plus 2y plus z equals 4. So these are linear equations in three variables x, y and z. We have to solve these equations by matrix method. So first of all, let us write these equations in the matrix form. So first will be the coefficient matrix 3, 1, 2, 2, minus 3, minus 1, 1, 2, 1 multiplied by the variable matrix x, y, z equals the constant matrix 3 minus 3, 4. We name the coefficient matrix A, the variable matrix x, and the constant matrix B. So A multiplied by x equals B. That gives us x equals 1 by A into B, which will be x equals A inverse multiplied by B. So we need to find A inverse, and B is available to us, which is this one. So for finding A inverse, we first write the cofactor matrix of A, which will be, first we will write the proper signs. They will be plus, minus, plus, minus, plus, minus, plus, minus, plus, which are alternately plus and minus. Next, we will write the values of the minors of these elements. So they will be minus 1, 3, 7, minus 3, 1, 5, 5, minus 7, minus 11. So that the cofactor matrix becomes minus 1, minus 3, 7, 3, 1, minus 5, 5, 7, minus 11. So this is our cofactor matrix. Now from this cofactor matrix, we will write adjoint of A, which will be transpose of the cofactor matrix. So that will be minus 1, 3, 5, minus 3, 1, 7, 7, minus 5, minus 11. We need value of determinant of A, so that can be easily calculated, and it will be 8. Now we have the formula for A inverse as A inverse equals 1 upon determinant of A into adjoint of A. So it will be 1 by 8 multiplied by minus 1, 3, 3, 5, minus 3, 1, 7, 7, minus 5, minus 11. So this is A inverse. Now we have this x, which is the variable matrix x, y, z equals this A inverse multiplied by matrix B, which is this one. So we write 1 by 8 multiplied by minus 1, 3, 5, minus 3, 1, 7, 7, minus 5, minus 11 multiplied by this matrix B, which is 3, minus 3, 4. It will be 1 by 8 times this matrix multiplication works out to be 8, 16 minus 8. That gives us the variable matrix x, y, z as 1, 2, minus 1. Now, by equality of matrices, we can equate the elements of the variable matrix and the column matrix 1, 2, minus 1. And we get the values of x, y, z, or the solution of these linear equations as x equals 1, y equals 2, and z equals minus 1. So this is the solution of these three linear equations in three variables x, y, and z. Friends, if you like this video, please click the like button. Share this video with your friends and classmates. Do subscribe this channel to get more videos of this type. See you in the next video. Until then, keep watching Number Collage. Thank you.